The overall goal of this methodology is to prepare a solid-state nanopore for biomolecular sensing experiments by precisely controlling its size and reducing its ionic current noise characteristics. This is achieved by first mounting a solid-state nanopore chip in a fluidic cell to establish a nanometer-sized channel between two electrolyte reservoirs. As a second step, a moderate electric field of approximately 0.01 volts per nanometer is applied across the nanopore to characterize its initial size and electrical noise properties. Next, high electric fields of approximately 0.3 volts per nanometer are applied across the membrane in short pulses in order to completely wet the nanopore, reduce electrical noise, and enlarge it to a desired size in discrete sub-nanometer steps. Results are obtained that show that a fully wet, functional, low-noise nanopore is produced based on analysis of the ionic current signal and successful translocation of biomolecules.
The main advantage of this technique over existing methods for controlling the size of the nanopore, like using a transmission or scanning electron microscope, is that it's performed in a salt solution using standard laboratory equipment in the same setup used for biomolecular detection. This ensures precise control of the actual nanopore size during biomolecular sensing experiments. The procedure also reduces low-frequency electrical noise and allows for clogged nanopores to be rejuvenated for further experiments.
This video assumes a nanopore chip has already been mounted in a nanopore cell. The next step is to prepare the cell for experimentation. To do this, place silver-silver chloride electrodes in each reservoir. Then connect a low-noise current amplifier between the reservoirs of the cell. Put the entire nanopore cell assembly in an electrically shielded enclosure.